I'm a big fan of Bruce Lee, and Bruce Lee, the martial artist, and he had a very, very good movie which you should all watch if you haven't already, called Enter the Dragon. And I'll tell you more about Bruce Lee and his relevance to quantum mechanics soon. But for now, I want to talk about quantum mechanics proper. Today we're going to go through chapter 2, which is called Enter the Wavefunction. The title comes from Bruce Lee's movie Enter the Dragon. We're going to talk about three things. The first is about plane waves. Plane waves are, for quantum mechanics, what bricks are to walls. Walls are made out of bricks. Wave functions, which is a central way that we're going to describe quantum systems, about which we'll learn more today. Wave functions are going to be made out of plane waves. Walls are made out of bricks. Wave functions, the way we describe physical systems in quantum physics, are going to be made out of these objects called plane waves. When we add together bricks, we get a wall. When we add together plane waves, and the technical term is a Fourier integral, adding up plane waves to make arbitrary functions, adding up quantum plane waves to make arbitrary quantum functions, quantum wave functions, will give us so-called wave packets. Lastly, we want to interpret what we mean by this wave function, and this wave function is going to be denoted, as it has been for many years, by the capital Greek letter psi. So that's it for the broad brush overview of today's class. If anyone doesn't have the lecture notes, they're in the green box. So let's begin with plane waves. These bricks out of which we're going to make arbitrary quantum mechanical wave functions. By the way, this idea of building up arbitrary functions out of plane waves is not peculiar to quantum physics. It's used in every area of physics and almost every area of engineering. So this is, I think, of very generic importance. So plane waves, what are they? So imagine we have some wave which is filling all space, and that wave filling all of three-dimensional space will have a series of wave fronts, or wave crests. Yeah. And so here we see a series of wave fronts, and those wave fronts are going to be propagating in some direction. So these wave fronts, and I'm going to render these ideas more precise soon. I want to begin with the concepts and then render them mathematically precise in due course. A plane wave is going to fill all the space. It's going to fill all the space, and the wave fronts, the crests, are going to be a series of planes. That's why it's called a plane wave, because it has plane wave fronts. This wave is going to travel in some direction, and I'm going to denote the direction in which that plane wave travels by k. So this vector k denotes the direction in which the plane wave travels, and this vector k I'll call the wave vector, just as a piece of terminology. So here we have our wave vector describing our plane wave. Now these wave fronts of this plane wave, we actually want to describe our plane wave with a complex function, a wave function. What is the complex wave function that describes this plane wave? I don't know yet, but it's going to be a function of position in 3D, which I'm going to denote by the vector r, and it will also be a function of time. Now this is a complex number. At each point in space, at each instant of time, this wave function psi is a complex number. As you know, complex numbers, if we go to the Argand plane, if I have an arbitrary complex number, it's going to have a real part A and an imaginary part B. This is an arbitrary complex number, A plus IB. We could also imagine this complex number as having a magnitude given by the length of this line from the complex number to the origin. This complex number also has a phase, which is this angle here. So when we speak of the phase of a complex number, we mean this number here. When we speak of the phase of the wave function, just go to a particular point in space at a particular instant of time, and that's a click, right? That click happened at a particular position and a particular time. Go to a click to a point in space-time, and the wave function is a complex number. Its phase will be this thing, and that phase will, since the wave function depends on position and time, this phase will depend on position and time. What's the relevance of this? It's as follows. These wave fronts are surfaces of constant phase. So these wave fronts are going to be surfaces at each point of which the phases are constant. So for example, this wave front would correspond to the phase having a particular value, having a particular value. Each of these wave fronts corresponds to the phase having a particular value. Now at this point you should be a bit pissed off for the following reason. I'm dogmatically making statements, and you should never take anything that I say ever on faith without actually proving it to yourself. But I'm going to continue making some dogmatic statements regarding these plane waves, because I'm going to ask you to prove all those statements in exercise 7. Yep. So take nothing on faith from me, treat everything I say with scepticism until you've believed it yourself. But what I want to do here is to give you an overarching picture of several results pertaining to plane waves, these bricks out of which we'll build arbitrary wave functions in due course. But you need to prove all these statements. So these wave fronts are planes, they're surfaces of constant phase. And so if you have a series of wave fronts, for example, A, B, C, and D, etc., then the wave front A would be a surface of constant phase corresponding to, let's say, naught. Wave front B would be the phase being 2 pi, 4 pi, and so on. Notice that this number is increasing in jumps of 2 pi as I go from wavefront to wavefront, and it's increasing in the direction in which the wave travels. Again, these are all statements which you'll prove in exercise 7. And again, I want to emphasise that these exercises are an intrinsic part of the course. This plane wave is going to represent, by the way, one electron. It's a very artificial scenario, one electron that fills the whole universe and it travels in one direction. It's completely delocalised, it's filling all the space. This electron will have a momentum p, which is proportional to the wave vector k. This is a lowercase k, and here's Planck's constant divided by 2 pi. This wave vector k has a magnitude, which we denote by the scalar k. K vector is the wave vector. K scalar is called the wave number. So K scalar is the wave number, and it's 2 pi on the wavelength. This is the wavelength of the electrons, the de Broglie wavelength, or the de Broglie wavelength. So the de Broglie wavelength is lambda, and lambda is the spacing between these wave fronts, between these surfaces of constant phase. So the wavelength is the distance between any two consecutive wave fronts. And this is the wavelength of this very artificial plane wave function. And we're going to be, by the way, just as you add up bricks to make a wall, we're going to add up these plane waves to make arbitrary wave functions. So what is the mathematical description of this wave function? Again, I'm just going to write it down. Again, you should take nothing I say on faith. You need to prove all these assertions, these dogmatic assertions, as a consequence of this mathematical definition. So here we have the dot product of the wave vector k and the position vector r. Here we have angular frequency. This is an omega, not a w. This angular frequency is related to the energy E of the wave in the usual way. And I claim that this function here describes the plane wave mathematically. But how do you extract all these pictures and concepts and assertions out of this single expression is something for you to do in exercise 7. Another point, this wave is travelling at a certain speed. It has a momentum p equals h bar k. Yep, that was its momentum. I'll write it down again. But we know that momentum is mass times velocity. Hence, the velocity, the speed at which these wave fronts move, is going to be h bar on m times k, m being the mass of the electron. That's all I wanted to say about plane waves. Again, I'm going to ask you to prove this in exercise 7, taking this object here, namely equation 10 as a starting point. So that's it for plane waves. Now let's add bricks to make walls. Let's add plane waves to make arbitrary wave functions. And by the way, I'm conscious of the fact that I've yet to give some more precise interpretive statements regarding the meaning of the wave function psi. We'll do that in section 6. So slightly roundabout logic, I want to start making wave functions psi that describe a quantum system before I actually start interpreting it. I'm doing that because that's what's done historically. I also think it's a more logical order in which to present it, but I'll see what you think. So we want to make wave packets, which for now I just want to describe or define loosely. I'll make it more precise soon. A wave packet is going to be an arbitrary wave function, an arbitrary complex number psi, which is a function of position and time, that's going to describe a quantum system, more precisely a single particle quantum system. Now I keep rabbiting on about bricks. Walls are made out of bricks. Add up the bricks, you get the wall. Now I want to introduce these two ideas of synthesis and decomposition, which lie at the heart of what I'm about to do. When I look at a brick wall and think of it as a sum of bricks, I'm decomposing that object. The brick wall is a sum of bricks. That can help me understand a complicated object by breaking it up into a sum of simpler objects. As another example of such a decomposition, if someone plays a chord on a piano or on a guitar, you can think of that as a sum of notes. You're taking the object, the waveform coming out of the piano, and you're decomposing it mentally as a sum of notes. And that can help you better understand that as a physical system. A third example, light is filling this room. It's white light, but we could conceptualize it. We could decompose it as red light filling the room, plus green light filling the room, plus blue light filling the room. The only trick is that there's an infinity of different colours. We can view the white light as a sum of every single possible colour of light, each of which fills the whole room. Yep. So this is another example of decomposition. The opposite process is synthesis. Add up the light of every colour and you will get the light filling this room. Add up every brick and you'll get the wall. Add up every note and you'll get the chord. So synthesis and decomposition. There's also a degree of arbitrariness here. How you mentally decompose something is up to you. So as a trivial example, I could choose to say that 6 equals 4 plus 2. And so you add 4 and you add 2 and you get 6. But I could also say that it equals 3 plus 3. What are the constituent bits? Is it 4 and 2 or is it 3 and 3? Well, it's up to you. It's a choice. Now this is a trivial example. A less trivial example might be how you describe a vector. Do you use Cartesian coordinates or polar coordinates? And the answer is do whatever the hell you want. But the pragmatic answer is do whatever you want and choose the way that makes your life easier, that makes your calculations simpler, that makes the answer appear more directly, that makes the problem more tractable, that makes the physics more visible or more manifest. And choose a representation that makes your life as simple as possible. So decompositions are in no way unique objects, and in some sense these are mental constructs that help us understand things. How do we decompose a wave function? We're going to decompose a wave function as a sum of plane waves. Now I've introduced numbers. I like numbers, I like the theory of numbers. If I wasn't a physicist, I'd like to think I'd be a mathematician. I value in both areas equally. So let's consider numbers. Let's consider the number pi. Now the number pi can be defined purely geometrically. Draw any circle, take its circumference, take its diameter, divide the two and you get pi. That's a purely geometric definition of pi, essentially as a circumference divided by diameter. Now we could choose to represent that number pi in the decimal number system, and when we do so, base 10 system, what we're doing is we're saying 3 times 10 to the naught plus 1 times 10 to the minus 1 plus 4 times 10 to the minus 2 and so on. So if I was to write it formally as a sum, I'd have a set of integers, c subscript m, and I'd have a set of powers of 10, 10 to the power of m, and m would go from minus infinity to infinity. This is how we would represent an arbitrary number in the base 10 decimal system. So this bunch of numbers, 0, 0, 0, 0, 3, 1, 4, 1, 5, 9, 2, 6, etc., is a way of representing, a way of breaking down, a way of decomposing this object, and that can be helpful for calculations. We could also choose to represent that same number in a different system. For example, the binary system, different integers, and here the integers are chosen from the numbers 0 through 9. Here the integers are going to be chosen from the numbers 0 and 1, because this is going to be binary system. You can decompose it however you want and choose the way that makes your life easiest. As another example, Taylor series. When I take an arbitrary well-behaved function f of x and write it as a Taylor series, I have a bunch of coefficients. I don't know, f subscript m, and these are now real numbers. And then powers of x. Well, I'm decomposing an arbitrary function as a sum of powers of x. When I do a Fourier series, I'm doing the same thing, except I choose a different thing to decompose over, which is going to be e to the imx. Sorry, that's a bit illegible. E to the imx. So these are the bricks. Yep, I put one brick here, I put one brick there, I put 3 bricks there, I've got a brick wall. I have 3 times 10 to the 0, 1 times 10 to the minus 1, and so on. I've got pi. I could also write pi in binary. I could write an arbitrary function f. You give me these bunch of coefficients. I'll take x to the naught and multiply it by 2. I'll take x and multiply it by -6. I'll take x squared and multiply it by 0. I'll take x cubed and multiply it by I and add them all up. And I'll synthesize an arbitrary well-behaved function f of x. Similarly with Fourier series. Decomposition, on the other hand, I tell you what the function is, and I want you to decompose it as a sum of powers of x. That's equivalent to the question of, here's a function, tell me it's Taylor series. Similarly, here's a function, tell me it's Fourier series. Similarly, here's a wave function, tell me how to decompose it as a sum of plane waves. I want to introduce 2 terms from linear algebra. The first is the idea of a basis. The bricks are the basis, right? You can make an arbitrary with arbitrarily fine precision. You can get any real number and write it as a sum of powers of 10. The set of powers of 10, namely 10 to the 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1, etc. That set of numbers, which you can add up with appropriate weighting coefficients, is spoken of as a basis. The powers of 10 are the bricks out of which you build a number, represented in the decimal number system. The set of all powers, non-negative powers of x, is the bricks out of which, the basis out of which you build an arbitrary function f of x via a Taylor series. When we speak of a basis as being complete, if you can build any wall out of a brick or set of bricks, then that set of bricks is complete. You can build anything with that set of bricks. If you can build or represent any real number, the set of powers of 10 will let you represent any real number. Sure, if you want arbitrarily high precision, you'll need arbitrarily many powers of 10, but that doesn't change the argument. The set of powers of 10 is a complete set for decomposing the real numbers, because any real number can be represented with arbitrary precision as a set of powers of 10. Similarly, the set of powers of x is a basis, and similarly the set is a complete basis, and similarly the set of Fourier harmonics, e to the imx, with m being any integer, is complete, that you can make any function out of a weighted sum of these objects. Now comes the hard bit, not the hard bit. This basis is countable. You have the set of powers of 10 and you can count them on your fingers. Okay, you need infinitely many fingers, but you can still count it. There's a countable infinity of these things. There's a countable infinity of these things. And the fact that this is countable and infinite is represented in the fact that this is a discrete sum, namely capital sigma. But when we're adding up plane waves, if this is a wave vector, if we want to add up plane waves to make an arbitrary wave function, we need to add up plane waves with every possible wave vector. And there's a continuous infinity of them. I've just gone through infinitely many wave vectors in going from the initial to the final point. Right? So we're adding up a continuous infinity of plane waves. This is not a discrete basis, this is a continuous basis. Now when we're adding up a countable set, we use sigma. When we're adding up a continuous set, which is necessarily infinite, instead of Greek S for sum, discrete sum, we use a Roman S for sum, and that's an integral sign. And an integral sign is nothing more than a continuous sum to be counterpointed with a discrete sum. So now we want to cut to the chase and represent an arbitrary wave function as a sum of plane waves. Now I'm going to state without proof that the set of all plane waves, the thing in the box on the left here, is a complete basis. In other words, an arbitrary wave function can be written as a superposition of all possible plane waves. How do we label each plane wave? We label each plane wave with a wave vector k. The set of all possible wave vectors k describes the continuous infinity of all possible wave functions. So now let me write down the most important equation in the course. I want to... That's inauspicious. I'm actually slightly superstitious, by the way. That's disgraceful, given that I'm a scientist. That's not a good sign. All right. So this is our plane wave, e to the power of I, etc. And I want to add these up. If I was talking about light, okay, each plane wave would correspond to a particular energy and therefore to a particular colour of light. Yep. Each plane wave would define a particular energy. You tell me the wave vector, I'll take its magnitude to give you the wave number. There's been a Doppler effect and white has become yellow. I'll tell you the wave number. You tell me the wave number and I'll tell you the wave length, because lambda is a function of k. You tell me the wavelength and I'll tell you the frequency mu. And if I multiply the frequency nu by 2 pi, I'll tell you what omega is. And if you know what omega is, you know what E is. So if we were talking about light, and the analogies between visible light, optics, and quantum optics, and quantum mechanics are direct, the mathematics is actually identical in many levels, including this. So if I had light of a particular energy, a particular wavelength, a plane wave would be like a red laser beam filling all space going that way. And I might add 2 times this red plane wave, plus 6 times this red plane wave, times I times this red plane wave, plus -6 times this yellow plane wave, plus 23 times this purple plane wave, and so on. Adding up plane waves of every single possible direction and every single possible colour would let me synthesise an arbitrary light field filling this room. Same thing here. So here's one plane wave of a particular colour, a particular energy, a particular k scalar. It's also going to be travelling in a particular direction given by the direction of the wave vector k. So this is one plane wave. I now want to multiply this plane wave by some number. Remember I said 6 of this plane wave plus 23 of this plane wave plus -1 of that plane wave plus I of that plane wave. So I need to multiply this by a number. This wave vector k specifies a plane wave. Yep. So I want to weight this thing with a particular number, and I'm going to call that psi tilde. But this weighting coefficient, this number, that I'm going to multiply this particular plane wave by, I want 6 times this particular plane wave. That weighting coefficient will be a function of k. Different plane wave, different k, different weighting coefficient. Now I'm going to write the weighting coefficient in 2 bits. Remember we have infinitely many plane waves, so each of our weighting coefficients had better be infinitesimally small. Each of our weighting coefficients had better be infinitesimally small. So dk, this is terrible notation, this is not a vector, this is dkx, dky, dkz. We write our wave vector in Cartesian coordinates. It will have Cartesian coordinates k subscript x, k subscript y, and k subscript z. So this is a little volume element, this is a scalar. I could write it as dkx, dky, dkz, but for compactness I write it as dk vector, even though it's a scalar. So this product of these 2 underlined functions is the weighting coefficient, and the fact that dk is infinitesimal makes my weighting coefficients infinitesimal, because I better be weighting all these plane waves by something infinitesimally small, because if it wasn't, when I added up infinitely many of them, this would diverge. So this is nothing more than one particular plane wave multiplied by one particular arbitrary infinitesimal weighting coefficient. And then I just want to add them all up. And if you add them all up, that's an integral sign. And since there's 3 variables here, it's a triple integral. But this is nothing more than a triple sum. It's a triple continuous sum. And this has let me synthesize an arbitrary wave function. Excellent. This is equation 15. The plane waves are a complete basis, and so we can synthesize an arbitrary wave function out of this sum of plane waves. By the way, the proof of the completeness of the set of plane waves as a basis is beyond the scope of this course. All right. So this again is the key equation of this course, adding up plane waves to make arbitrary wave functions. One small extra thing. There are several occasions on which I'll introduce some pointless complication just because it's convention. And the pointless complication is to put a constant here, which is 1 over 2 pi to the power of 3 on 2. And this is purely historical convention. There's no consensus in the literature. I've just chosen one particular way of doing this, which is this way. So this is just a purely pointless convention constant, which just serves to re-weight these weighting coefficients. Again, the analogy, you listen to someone play a chord on a piano, and you think of it as a sum of notes. Here we see an arbitrary plane wave, an arbitrary wave function, and we think of it as a sum of plane waves. This object here, by the way, is called a Fourier integral. When you express arbitrary functions as sums of plane waves, that is a Fourier integral. This is synthesis, adding up plane waves to give an arbitrary function. This object here can go by a few names. If I was teaching mathematics, I'd call it the Fourier transform of the wave function with respect to position. But for this course, I'm going to call it something different. I'm going to call it the momentum space wave function. Where does the word momentum space come from? Well, K is essentially momentum up to constants. And so this weighting coefficient, which I'm calling psi tilde of K, is also a function of momentum. It's called the momentum space wave function. I want to return now to a point that I made earlier, and that is how you choose to decompose an object, a complicated object, is up to you. You can work in spherical coordinates or Cartesian coordinates. You could choose to express a physical system in one way or another. This can be viewed as a machine. If I give you this object here, this momentum space wave function, you can shove it into this integral and out will pop the wave function. So which is the system? Is this the system or is this the system? And the answer is neither. It's up to you. You could say that this object is the wave function to describe the system, and this is just an auxiliary that you use to synthesize the arbitrary wave function by adding up plane waves. Or you could take the opposite perspective. You could say, well, this actually represents a system. If you tell me what this is, and you can shove it into the integral, then you tell me what it is. These are two different ways of representing the same object. I've just taught you how to go from here to here, which is a process of synthesis, but you could also ask the opposite question, how do you go from here to here? And that's the process of decomposition, and that is written down in equation 16. Equation 16, I won't write it down here, but this lets you go from this lets you go from the momentum space wave function to the real space wave function. This is real space. Equation 16 lets you go the opposite way. So synthesis, decomposition. Equation 15 lets you go from the Fourier space representation or the momentum space representation of the wave function to the real space representation of the wave function. Equation 16 tells you how to go in the opposite direction. These are two different ways of representing the system. That also begs the question, is one way better than the other? Well, no. There's infinitely many ways to represent any system. We're actually going to learn soon enough how to represent a quantum mechanical system, not just in two different ways, but in infinitely many ways. Yep. And remember also, the physical world doesn't know about quantum mechanics. When an electron does its thing around a hydrogen atom, it doesn't know the Schrödinger equation. It doesn't know anything about differential equations or quantum physics, but it still does its thing. The point is, and it's an important one, the physical world exists independently of how we choose to describe it. And the fact that we can mathematise a quantum system, not just in two different ways, but in infinitely many ways, we can represent the quantum system and describe it precisely mathematically in infinitely many ways, is a manifestation of the fact that electrons don't know how to do quantum mechanics. They just exist and do their thing. Question?
In momentum space wave functions, is that independent of
So the question is a momentum space wave function independent of time? And the answer is yes. So there's a certain dissymmetry here that this wave function is a function of position and time is 4 variables. This wave function here is only 3, but absolutely this is purely independent of time. And the reason it's independent of time is that in some sense time has been integrated over. Time doesn't exist in this space. If you tell me the wave, in order to if something's oscillating, evolving in time, it's going to oscillate at a particular rate which determines its energy. Yep. If something's oscillating, it'll oscillate as cos of omega t. But omega is related to energy because omega equals E on h cross. So how something evolves in time tells you about its energy, but its energy is related to its wave vector. So when you go to the momentum space, in some sense time doesn't exist because you've integrated over time to get a function of k, which is also a function of energy. And energy tells you how things grow old in time, but absolutely there's a dissymmetry here. Strictly speaking, this is not, this is a form of Fourier integral, but this is not the most general form of Fourier integral. If I was teaching mathematics, I'd have the same number of variables here, but because this is a quantum system, I need time here, but I don't need time there. It's a very good question. So note that dissymmetry, and I should have pointed it out earlier. There's a time here and 3 variables, but there's just 3 variables and no time here. That's all I wanted to say about how to go from plane waves to wave packets. Though I've not yet told you what a wave packet is. Now the machinery of adding up plane waves to synthesize arbitrary functions or decomposing arbitrary wave functions as sums of plane waves is the business of Fourier analysis. In fact, it defines Fourier analysis. And I'm aware that some of you, for some of you, you're meeting these ideas for the first time. For some of you, for example, particularly those doing double degrees in engineering, you're meeting this idea for the 15th time. The reason you're meeting it for the 15th time is because it's bloody important and cuts across all knowledge, all quantitative knowledge, but it's also a bit of a pain in the arse because you've got to sit through it all again. But I hope that I give you some additional insights, and I need to I need to be fair to everyone, hence to do it from first principles. So exercise 9, which I'm going to go through in the tutorial this afternoon, is what I call the full Fourier analysis toolkit. So the full Fourier toolkit. Everything that you need to know about expressing wave functions as sums of plane waves and the opposite. Everything you need to know about plane waves in the context of quantum physics in the context of my course. I'll teach you everything you need to know from first principles through going through exercise 9 in full in the tutorial. So that's an important one. I'm not going to go through exercise 9 now, nor am I going to mention the equations because we'll go through it in full in due course. I want to close off this section by talking about wave packets because I haven't told you what that is. These things are very artificial. They fill all of space. Nothing fills all of space. Any real physical system has a finite extent. So let this be some egg shape in 3D, and the system exists inside this egg, inside this sphere. So real quantum systems will have wave fronts, and those wave fronts are not necessarily going to be planar. They'll in general be warped in some way, and these systems are going to propagate through space. It's like some fuzzy ball. If you're thinking I'm being a bit vague, that's because I am, but I promise you that we'll get more precise soon. But for now, let me make the vague statement that this is like a fuzzy snowball or a fuzzball propagating through space. Classically, we chuck a tennis ball and it follows some trajectory in space. Quantum mechanically, we're going to have this fuzzball rather than a point particle. And this fuzzball can propagate through space. It might spread, it might move through some trajectory. What do we mean by its trajectory? Well, the centre of mass of a particle. This will have some centre of mass, denoted x. We'll learn how to calculate it soon. And this centre of mass may evolve with time along some trajectory, depending on the forces which are applied upon it. So this is what we mean by a wave packet. It's a packet of waves. It's a sum of plane waves. It's a packet of waves which is in some sense localised. It doesn't fill all space. The plane wave is delocalised. It fills all space. This thing, on the other hand, is localised. So just as you can have your lunch in a packet, and that packet is not infinitely big, a wave packet is a finite-sized wave function. I now want to move on to the final section of today's class, which is about interpretation, section 6. This is about the question of what the hell does it all mean? Still a surprisingly controversial question in quantum mechanics. I want to split this up into a few bits. The first is the Born interpretation, named after Max Born. Quantum mechanics is probabilistic. Quantum mechanics does not obey the laws of determinism. If you throw a dice, you may get any outcome. If you roll a quantum dice, you have a particular quantum system with a particular wave function, and you make a measurement. For example, you have a camera, there's some wave function waving through space, and you have a camera. You take a picture, you might get a dot there. Then you do exactly the same experiment with exactly the same wave function. You do the same experiment and you get a dot in a different place. You do exactly the same experiment again, and you'll get a blip here. This is an example of the probabilistic nature of quantum mechanics. And that's what experiment tells us. And that probabilistic nature is counter to the idea of determinism. Deeply disturbing, deeply disturbing. But quantum mechanics is probabilistic. So this thing here, this wave function, must describe in some way, or have built within it somehow, a probability. So what Born said was, let's introduce what's called a probability density. So Greek symbol rho, this denotes a probability density. This is a probability per unit volume. Probability density, which is a probability per unit volume. And what Born said, as a way of interpreting the wave function, is that the magnitude squared of the wave function is the probability density. Now this cannot be derived from first principles. There's no exercise to prove this. This is just an axiom. I don't like saying that. I'd like to be able to say, here's how you prove it. But all I can say is something much less satisfactory, which is this gives consistent results with experiment. And it disturbs me that I can't derive it from first principles. But there's a lot of ad hocery, there's a lot of ugliness at the foundation of quantum mechanics where we make dogmatic assertions because we can't derive it from first principles. If we could, we would, but we can't, so we don't. We'd love to be able to. Contrast this, for example, with a special relativity course. Much more like mathematics. You start off with a few axioms, and then you derive everything from first principles as logical consequences of those axioms. Quantum mechanics is not like that. Quantum mechanics foundations have pieces of ad hocness, pieces of ad hocery stitched together, and I won't make any bones about that, and I'll try to reveal the full patchwork nature of this. This is one example of a dogmatic assertion which is ultimately justified or not by its consistency with experiment. All right, so this thing is called a probability density, more precisely a position probability density, but let me just call it a probability density. And since it's a probability density, it's a probability per unit volume. So what does this thing mean physically? Well, what it means physically is let's choose a particular point in space. So let's freeze time at some particular time, let's call it t0. Let's choose some particular point in space at that instant of time. This object here, and this particular position, let me call it r0. So let me just call it r, and let me call the time t. Sorry about that. So what does this probability density mean? Well, let's choose this particular point, described by position vector r. Let's erect an infinitesimal box here. And this infinitesimal box will have volume dx, dy, dz, which I'll denote as dr. Now this is a probability density, it's a probability per unit volume. If I multiply probability per unit volume times a probability times a volume, then I get a probability. Just to repeat, a probability per unit volume, a probability density, multiplied by a volume is a probability. Probability of what? It's the probability, this is it, this is the Born interpretation. This object here, which is the same thing as the magnitude squared of the wave function, times dr. These things here this is the probability of finding an electron at this time in a little box of volume dr centred at this position r. So just to repeat, this object here is the probability that at time t, and you find the electron to be within this box. If you choose to measure that, that'll be the probability of finding the electron in that box centred at position vector r at time t, and the box has an infinitesimal volume dr. This object here will be infinitesimal because the box is infinitesimally small. So I've just argued that this is the probability of finding the electron in the box at a given instant of time. What's the probability of finding the electron anywhere? Well, you just add up all the probabilities. Now, if this is going to describe one electron, and all the quantum mechanics we'll do in this course is going to describe one electron systems. There'll be one exception, which I'll point out in due course. This is a probability of finding an electron in a particular box at a particular time. This is a probability of finding an electron anywhere at a given time, and that probability must be 1. So this is spoken of, this is a condition that a wave function must obey, and this is spoken of as a normalization condition. Just says the probability of finding an electron somewhere is always 1 if you have one electron. And this is equation 22. Now, if a wave function does not obey this property, you can always force it to obey that property by redefining or scaling the wave function according to equation 23. The next thing I want to move on to is superposition principle. This is the second of 3 things I want to talk about in the context of interpreting quantum mechanics. Now, suppose you take ordinary matter, such as my fingers, and suppose I was to say that this is a valid state of a physical system, and this is a valid state of the physical system. Is the superposition of the two a valid state? No, because my fingers don't pass through each other. So if this is a valid state of the system, and this is a valid state of the system, you can't just add them together to get a valid state, because my fingers can't pass through each other. However, if you have light beams, it's a different story. If light beam A is a valid state of the light field by itself, and light beam B is a valid state of the light field by itself, then if you add the 2 light beams together, then they can superpose. The 2 beams will pass through one another. So this is the idea of superposition. And quantum mechanics has something identical. Suppose that this is a wave function that describes a quantum system. It's a function of position and time. I won't write that down for simplicity. Suppose that that same quantum system can be described by a second wave function, psi b. The superposition principle says, this is counterintuitive in the fact that you can't pass fingers through each other. Superposition principle says that if psi A is a valid quantum system and psi B is a valid quantum system, then the superposition of the two, the sum of the two, is also a valid quantum system. The Fourier integral is actually an example of this, because this is nothing more than a sum of plane waves. Each plane wave, as we'll see, will obey the underlying equation of quantum mechanics, the Schrödinger equation. And if any one plane wave obeys the Schrödinger equation, the linearity, I'll explain this later in a later lecture, the linearity of the Schrödinger equation means that a sum of plane waves is also a solution. This is superposition principle. It's going to be reflected mathematically in the fact that the Schrödinger equation is a linear equation. In other words, it obeys a superposition principle. If this is a solution and that's a solution, then the sum of the solutions is a solution to a linear equation. That's not true for nonlinear equations, such as that which governs fingers, or general relativity, or condensed matter physics, and so on. A direct consequence of the superposition principle, which I'm going to be examining, by the way, in an assignment, which will come out within the next couple of days, assignment 1 of 2 for this unit. Let's ask the question, let's add together 2 wave functions. And let's ask the question, what is the probability density of the sum of the 2 wave functions? Well, this is a combined wave function. This is a probability density. Now, one point. If you're at all rusty on complex numbers, you'd be immensely benefited by spending half an hour revising complex numbers, because this course is full of complex numbers, complex functions. To take the magnitude squared of a complex number, for example, you take that complex number and you multiply by its complex conjugate. So you do very well to spend half an hour revising complex numbers. You'd also do very well to spend half an hour revising vector analysis, and similarly for linear algebra. So complex numbers, vector analysis and linear algebra are both used throughout this course relentlessly, and I expect you to be fluent with all of them. So here's the probability density of a sum of wave functions. Psi A star is the magnitude of psi A star squared, which is the probability density of wave function 1. Psi B star times psi B will be magnitude of psi B squared, which is the probability density of wave function B. But then we get these cross terms, psi A psi B star plus psi B psi A star, which I can put together in this term here. This object here actually represents interference. Interference, for example, in the context of the Young's two-pinhole experiment. So interference is a direct consequence of both the superposition principle together with the complex nature of wave functions. Final thing I want to consider is the correspondence principle. As I often like to say, a new theory, a higher theory of physics must reduce to the old in the domain of validity of the latter. Now that's important, so I'll say it again. A new theory, a higher theory, should reduce to the old in the domain of validity of the latter. In the context of quantum physics, we need what's called the correspondence principle, which simply says that quantum mechanics, QM, must reduce to classical mechanics when you're describing systems for which classical mechanics is fine. So the demand that quantum mechanics should reduce to classical mechanics is known as the correspondence principle. As an example, here's a billiard ball travelling through space along some trajectory, moving from the point A to the point B. That's classical, that's fine. I'm throwing a billiard ball through the air, through a gravitational field. What would I do quantum mechanically? Well, quantum mechanically, I'd have a wave packet, a flying fuzzball. That flying fuzzball would have a centre of mass, which we'll learn how to calculate. And that centre of mass will follow some trajectory. And if that flying fuzzball happens to be a billiard ball, it had better obey the laws of classical mechanics. It had better obey Newton's mechanics. Question, how do you extract Newtonian mechanics from Schrödinger mechanics? Good question, we'll do it as part of our course. Question, how do you conceptualise that transition from quantum to classical? Well, the fuzzball gets ever smaller. How do you render that mathematically precise through a deep understanding of the Schrödinger equation? Excellent question. Section 6.4, I set that to you as homework. It'll take 3 minutes to read. Our next lecture will be the Schrödinger equation, chapter 3. Thank you.